In this tutorial, we're going to go over force coefficients and scaling related to aircraft. I just want to go over the basic theory here, and we'll have some follow-up lecturettes, one examining Reynolds effects on lift, and another one where we'll work a few problems to quantify things. We'll start off with some nomenclature. We'll be talking about some of the geometry of the wings will be used in these force coefficients, so I want to make sure that we've properly defined them. This is a wing section, as we discussed in the first lecture. That is the two-dimensional slice of the wing. And so this would be in the XZ plane. This slice right here, the leading edge is defined as the first part of the wing that the flow sees. The trailing edge is the last part of the wing before it passes on. The chord is the distance between them, and that is often noted little c, chord with a h in it, chord. The wing has a chord line, which we see right here. Basically, this line represents the position in the intermediate point along the chord between the upper surface and the lower surface here, is defined by that dashed line. We also have a line connecting directly the leading edge to the trailing edge, and that is the solid black line right there. If the dashed line is deflected from the solid line, that means we have camber, that there's asymmetry to the wing, upper-lower asymmetry to the wing, not fore-aft, but up and down in the z direction, and that asymmetry is known as camber. An extreme example of camber might look something like this, where the wing is essentially bent relative to the mean line, or relative to a line connecting the leading and trailing edge. You could think of something like a sail. Where those lines coincide, you have a symmetric foil with zero camber. Symmetric foils are not commonly used in aircraft. We'll see why. You do see these in some cases. A classic example of this is a sailboat keel. When a sailboat is sailing, you have little wings, which are the sails. The sails generate significant side force along with some forward force. That side force has to be counteracted, and is counteracted by a keel, which is actually under the hull. This is a side view of the hull. The keel sticks down like this and often has a counterweight, which is counteracting the buoyancy of the boat. That thing right here is known as the keel, and that actually creates a side force that opposes the side force generated by the sails. In fact, they're in equilibrium. It is a lifting surface by definition, and over time, with the development of sailboats, things have progressed where they started using better and better, more and more efficient sections compared to, say, what the Pilgrims had, or even prior to that, that enabled sailboats to sail more efficiently. Because they have to produce side forces in both directions, sailboats don't have a specified direction, that foil has to be symmetric, because sometimes it's generating lift this way and sometimes it's generating lift this way, and it's about 50-50. Aircraft only, generally speaking, have to generate lift in one direction, so they can be asymmetric, and there is, as I said, value to that asymmetry that we'll come to study in the class. The top, so a key dimension here is the chord C. That's a length scale, and then from the top view, so this is in the XY plane, you have a top view of the wing. This wing has some area in the top view, and that area is usually noted S, and we'll use that as a area scale, a typical area scale. There's a length scale associated with the planform view, with this view, which is the span. It's the distance from one side of the wing, say the starboard side, to the port side of the wing, or tip to tip. That's the span. So that's another length scale. So you have two length scales here: the chord, you have the span, and you have the wing area S, which is a surface area, or of dimensions length squared. All three of those would be important characteristic values that we will see repeatedly in most of the formula that we will get into this semester. Now, in terms of describing a wing like this, in terms of its thickness and positions of camber. We'll discuss that more in the week prior to spring break. The wing generates forces. We have a lift force, which by definition is normal to the free stream flow. So if the free stream flow right here, the relative velocity v infinity to the wing is coming in from left to right, then the lift is straight up on the board here, L vector. And we have a drag force, which is parallel to that flow in the downstream direction, and that is the drag force here. And the resultant of those two is the is shown here is this R vector, is the resultant of those two forces. It points up and back, and obviously the more efficient foil would be producing more L relative to D. The resultant force would be closer to L. That is the goal, generally speaking, in most aircraft design. We also have shown here a normal force. So if this is the chord line of the foil right here, then we can define a deflection of that relative to the free stream, which is alpha, which is an important angle known as the angle of attack. Be cautious this semester as we move forward that alpha will show up quite often. When it's in a formula, treat it as radians. For example, we often take sine alpha. Sine alpha, when alpha is small, is approximately equal to alpha. That's known as the small angle of approximation. We'll see that a few times during the semester, where there was a sine alpha and it becomes an alpha, but the alpha in that formula is radians. If you put degrees in, you will get a remarkably strange answer. And hopefully that would tip you off. So we have the angle of attack. That's a deflection of the chord line from the free stream flow. We have lift normal to the free stream flow. We have drag parallel to the free stream flow, and we can write these in terms of these two components, N, which is a normal force normal to the chord line, and A, which is the force composed parallel to the chord line here. And we can write L in terms of N and A, and D in terms of N and A, and vice versa. We could also write N and A in terms of L and D if we wanted to. We also have a pitching moment. I mentioned already in a class that a common spot for the moments to be taken about is the quarter chord, and that is the position a quarter of the way between the leading edge and the trailing edge. A quarter of the way back is the quarter chord. That is a traditional point for moments, and that is because in thin airfoil theory, that is the point, that is your center of pressure. And typically speaking, the center of pressure is somewhere near there. And when we looked at the pressure distribution a few lectures ago, we saw why that is. It doesn't have to be exactly there, but it's somewhere near there. So that's a common point for moments. Sometimes you see moments about the leading edge, but typically about the quarter chord. And another important point is the convention. And a positive pitching moment tends to increase alpha. So if the pitch is trying to, if the resulting moment is trying to pitch it back, that is a positive pitching moment. For example, if the center of pressure was forward or upstream of the quarter chord, the result would be that it would be try to pitch the airfoil back, increase the angle of attack. That would be a positive pitching moment, as shown here by this convention, the arrow turning in that direction. So moments, of course, require an additional length scale to non-dimensionalize, and we'll discuss what that is in a few slides. So in traditional dimensional analysis, we take all the components that are of interest in the flow field that we believe affect the forces in the flow, and we try to relate them. And we try to relate them intelligently, such that we can reduce the number of common factors we have to get to. Drag is a force, so we have units of mass times acceleration, or kilogram meter per second squared in the case of our KGS units. We have, in this simple case of flow over sphere, we would consider some other important parameters. For example, what might affect the drag? Well, the diameter. We might think intuitively a larger sphere is going to have more drag. How fast it's going. It's going faster, probably more drag. The density probably is also going to increase with drag, and also viscosity. Now, this doesn't mean that there aren't other factors that may be important. For example, the speed of sound of the sphere might be moving near Mach 1. For example, does it matter if the sphere is rough or not? There's other factors that might come into play in terms of drag dependency. Here we're taking a very simple case where we aren't concerned. We assume it's a smooth sphere. We assume it's moving at low speed through a Newtonian fluid, and these would be the quantities of interest. So the drag will somehow depend on these particular things, du, rho, and mu, oops, and how it depends on those, how it comes to depend on those, we can look at through dimensional analysis. So basically it says, okay, d or other forces, we're concerned with drag here, is some kind of function of these things. And we can throw this into what's called dimensional analysis using Buckingham-Pi theorem and come up with this relationship between a non-dimensional drag, so here I've non-dimensionalized the drag, and a and in this case a single non-dimensional flow variable, a non-dimensional quantity right here written as u, a velocity scale times the length scale times the density divided by the viscosity, the dynamic viscosity of the fluid. And we can simplify this because we can write the kinematic viscosity of the fluid as just simply the dynamic viscosity, mu over rho, which simplifies it into this expression, which obviously at this point you might recognize as being a kind of Reynolds number. So here we have this Reynolds number, and again, this parameter arises if we take either a scaling analysis or even simply the Navier-Stokes equations and non-dimensionalize the terms of that equation. You find that the ratio of the inertial term, the nonlinear terms, to the viscous terms ends up being a ratio of this form: a velocity scale times the length scale of your problem divided by the kinematic viscosity, which is a property of the fluid. So two kinematic quantities, or kinematic, a geometric, and a property of the fluid. The left side we will manipulate. So this is one way to non-dimensionalize drag. Traditionally, instead of rho u squared, it's you use a half rho u squared. You use the true dynamic pressure. That is just convention. That half does not have to be there, but by convention it is there and will always be there. And what shall we use as to non-dimensionalize what length scale? So we need some length scale squared. So we could use the diameter squared. We could use the surface area of the ball, or the sphere rather. We could use the cross-sectional area of the sphere. We could use the radius squared. There's lots of different options. And so again, this is a convention thing. On the last slide I'll show you how that convention varies among different fluid disciplines. In this case we're going to use the cross-sectional area S of the sphere, and that would be used in this kind of, probably used for this study primarily because the nature of the drag is a large scale separation drag. It's a bluff body, and therefore the drag is strongly dependent on that cross-sectional area. The result of this expression shows us that we can relate this drag coefficient to one parameter, the Reynolds number. This is a huge simplification, relating these two non-dimensional quantities. It tells us a lot about the dynamics of the problem, and it tells us a lot about and enables us basically to study a problem, a single problem, and scale it to any other different kind of sphere, and that's a major advantage. Newton called this a principle of similitude, and in this case the important thing is you have you can achieve both kinematic and dynamic similitude. In that sense, this ball right here, the sphere right here, we have some smoke visualization of the flow going over this. We probably have some measurement of this in the wind tunnel, the drag. It's sitting on a sting. The sting could have a piezoelectric or a force transducer on it, telling you what's the drag on the sphere in the flow. And if we take a picture of this, this could represent either of these two cases. The sphere, that sphere could be 10 meters. The fluid could be moving 0.1 meters per second. The fluid could be castor oil. Or the sphere could be a centimeter in a fluid of 5 meters per second, a flow of 5 meters per second of fresh water. Both of those achieve the same Reynolds number. The two Reynolds numbers are exactly the same. And therefore, the flow, which depends entirely on that Reynolds number, the nature of the flow depends entirely on that Reynolds number, will be exactly the same. Now, if you were to go to measure the velocity, the actual velocity here, you would find it would be different in each case. You can, in the left case, the flow speeds are much smaller. It's going to be a smaller velocity for the castor oil case than the case of fresh water. So in actual numbers are going to be different, but in terms of non-dimensional quantities, it's going to be the same. And the streak lines and streamlines and flow patterns will be the same. The drag coefficients are going to be the same. And any of these non-dimensional quantities, for example, if you took u and divided by u infinity for both cases, the values would be the same. So in the process of non-dimensionalization, we collapse two very different problems on top of each other because they are in the same exact flow regime. the same, in this case, the same Reynolds number. And so this image could be either case. If you were given these two cases, say which one is that, you say I couldn't tell you because they are the same Reynolds number, and therefore they are the same in terms of the imagery. This allows you to do something like an experimental investigation where you take, could be castor oil, could be fresh water, whatever it is, you take your smooth spheres and you measure their drag and compute the drag coefficient against a range of Reynolds number. That's written capital R, but that should be RE, or Reynolds number. And you measure your CD, you measure your Reynolds number, and where S is this frontal area, or cross-sectional area, maximum cross-sectional area of that sphere, where D is the diameter. And you see you have this, in this particular measurement, you see the flow. As the Reynolds number increases, our CD is dropping, it flattens out, it drops quickly, and then it starts rising again. We'll talk about this a bit more, why it looks like this when we get into viscous flow. Just in summary, one thing to caution you, and I'll mention this again later, is that just because the drag coefficient is dropping does not mean that the drag is dropping. As you increase Reynolds number, let's say you keep everything the same, and we're only increasing Reynolds number via an increase in velocity, the Reynolds number will be going up. Here it says the drag coefficient's going down, at least for part of this range. In this range here, the drag's dropping. Drag coefficient is dropping. But remember, the drag itself is proportional to the velocity squared times that drag coefficient. So times CD. It has rho in there and everything else, which isn't changing. Cross-sectional area is not changing. So the drag's proportional to a U squared times CD. So even if CD is dropping with Reynolds number, U squared is going up with Reynolds number, and faster than CD is dropping. So ultimately the drag will rise, even if CD is dropping. There are places shown here in this phenomena where you actually have an increase in Reynolds number, which could be coming from an increase in flow speed, and you have what is actually a drag decrease for a very short reason. And this happens, this actually is related to a transition from laminar to turbulent. And spherical objects like this benefit from turbulent flow, which is one of the reasons that golf balls are dimpled, in order to push them into that turbulent world to drop their drag. And we'll discuss that more when we get to viscous flows. Having made this table, someone could come in and have their own smooth sphere for some totally unrelated application, nothing to do with what you're testing in the wind tunnel, but they have a smooth sphere moving through steady fluid, Newtonian fluid, and all you have to do is take the Reynolds number of your problem to get, might be right here, and you go up, get the drag coefficient studied in this tunnel. You take that drag coefficient and then you dimensionalize it using your dimensions, your velocity, your cross-sectional area, your density, and you have your drag. And that came from the single study of smooth spheres against the one parameter that controls their drag. You can use this for any application, and which is really where the power comes in. Also, as I mentioned, it helps you to understand the flow regime. Right here, when we get into viscous flow, we'll see entirely what makes this chart. Why is there the dependency, special dependency of the drag coefficient on this single parameter, and that is the dynamics of the problem. For our force and moment coefficients, when we're talking about wings in class, and we'll spend a little time with some other objects when we deal with propellers and fuselages, but for wings, we're going to use a very specific set of force and moment coefficients. We will have the dynamic pressure as is defined here, 1F rho U infinity squared, so that's a free stream dynamic pressure. The lift coefficient for that wing is going to be the lift of the wing, non-dimensionalized by the dynamic pressure, times a characteristic area. In this case, it's S. It's the planform area of the wing. It's not a cross-sectional area. It is not the surface area. It's roughly half the surface area. So this is basically, if you take the upper and lower surface, that's your total surface area. This is essentially half of that if it were pretty thin. So just be cautious about that. That is just the tradition that is used for computing the lift coefficient. For the drag coefficient, we'll use the same non-dimensionalization, Q infinity times S. Q infinity always appears in the denominator. It's just a question of what do we use for our characteristic areas or length scales if we're dealing with moments. When we include the moment, we will include also what's known as the mean chord. If our plan form of our wing looks something like this, maybe it's somewhat swept. Sorry, my monitor keeps going off. Somewhat swept, so the flow's coming in like this, and this might look like a typical wing that's a little shorter at the tip than it is at the root. This is the fuselage. Then the mean chord is whatever the mean value of that chord is. The root chord is here, is bigger than the tip chord. You take in a quadrilateral like this, you could just take the average of the two. If it's a more complicated shape, you'd have to integrate to find the mean. But anyway, here it's drawn something like this. So mean chord. It's a characteristic length scale that represents that wing. Is shown there. So this is from the moment coefficient. We will also spend a lot of time with 2D foils. And 2D foils don't have there's no surface area for a 2D foil. It's infinitely, it's in a plane, essentially. What we're going to essentially consider for these sections is that they extend to infinity. They're basically the section of a wing that extends to the infinity. And by extending to infinity, you eliminate any three-dimensional effects that happen. So that's how we're picturing our wing. Essentially is a planform area of infinity. So what we're going to be considering is not a lift. So these forces over here have units of newtons. They are forces. The forces you see here, L prime to D prime, are lift per unit span. They are lift per unit in the direction normal to the free stream, in the span-wise direction, in the y coordinate in our original definition of the coordinate system. So L primed has units of newtons per meter, because we only care about what's happening in that particular plane. What's happening in the y direction, we're assuming to be exactly the same all the way to infinity. So there's no variation in that y direction. We only have to study what's happening in one plane, but an infinitely thin wing in that sense has no lift. It can produce no forces. So we have to consider, well, we're basically multiplying that one unit in the y direction. And that will give us our force per unit. So force per meter into the board, into the plane, is what we're doing. So that means our denominator will have the same units. So here we do not need an area. There is no area we could have. So so we use the chord. And you could consider this as the chord times 1 unit into the board, if you want to think of it that way. So the non-dimensionalization for these lift sectional or foil lift coefficients is C, the chord, and you see that also in the denominator for the drag. So again, this is thinking 2D. By convention, these are commonly written as lowercase. See how this is a CL, this is a capital CL. They don't always use that convention, so be cautious. If you see the little CL, that generally means you're dealing with sectional lift coefficients. And a little CD and a little CM, and for CM we need a length squared, and here again we only have one length scale. There's no span length scale to work with, so we just simply square our single length scale that we have, which is the chord. So this chord squared. So again, this is a moment per unit width into the board, or Newton meters per meter, or actually works out to newtons, but it's easier to think of Newton meters per meter. So be cautious about this. I did note this. There's a little back and forth on that. Anything we'll see in X-foils is this stuff is being reported. X-foil is a 2D code. It looks at sectional things. It's reporting this column right here. And what we'll come to see when we get into 3D wings is 3D wings are made of foils. They're made of foils, and each of the foils might have a given lift coefficient. But what's the lift coefficient of the whole wing together? Is it the same as the lift coefficient of a section? Is it less? Is it more? And the deviation from the sectional lift coefficient comes from the three-dimensional effects that we'll study in class. And we will treat it as such. We'll essentially treat 3D lift as basically 2D lift, the 2D lift that's provided by the sections that make up the wing, plus some kind of 3D effects, which are generally speaking detrimental. So if we were to do the same non-dimensional analysis that we did for our sphere, for the aircraft it's a bit more complicated because we have to consider a couple of other things. One is, for a given wing, what is the angle of attack of that wing? Now that obviously has an effect on the drag, and that is a parameter that is very important to the aircraft, and one that we should be allowed to vary. We also end up with a kind of Reynolds number, and a third number because the speed of sound becomes an important property. The speed of sound is a fluid property, as is the viscosity, as is the density, as the kinematic viscosity. That speed of sound is an important property. It's when we study flows near Mach 1 or above Mach 1, we'll see that the Mach number has a drastic effect on the flow regime. When you're away from Mach 1, the Mach number really doesn't matter. You don't really care what the Mach number is. Once you get below Mach number 0.3, it's irrelevant to the problem. So we end up with these three kind of numbers in order to non-dimensionalize our lift coefficients, non-dimensionalize our drag coefficients. It boils down to these three parameters: angle of attack, Reynolds, and the Mach number. And if we want to achieve, as that experiment did with the sphere, if we were to have a wing and in tunnel where we had complete control over the Reynolds and Mach and angle of attack, we could study that. We could take a wind tunnel, we could keep Reynolds and Mach the same and vary the angle of attack. Change the Reynolds and do the same, and change the Mach, do the same, and build this three-dimensional function. CD is a function of those things, and then someone could come in and say, I'm interested in how the wing does at this particular altitude, at this particular speed, at this particular outside temperature, and this angle of attack, and you say, well, it's in my data. You interpolate it out of my data. The trouble is that it's hard to completely control the range of Reynolds and Mach and the tunnel, and so there are some restrictions on that we'll discuss in class as we move forward. So these three parameters are important, and because of the difficulties of really retaining Reynolds and Mach in the same wind tunnel experiment, for example, if you had a wing and you knew the conditions and you said, put this wing in the tunnel for me and run it at the same alpha, Reynolds, and Mach number, the good thing with that is the drag coefficient that came out of the experiment is the same drag coefficient as your wing's going to have in real flight conditions. As long as these parameters are the same, you have complete dynamic similarity, and CD at full scale in the air is going to be the same as CD in the tunnel if these three variables are controlled, and it's obviously the same geometry. But that's generally speaking not possible. It's not possible to have all three match your conditions for most cases. So then what do you do? Well, what you do depends really on what flight regime you're studying. If you're looking at, for example, low Mach number flow, you can say, I don't care what the Mach number is in my tunnel. If it's wrong, it doesn't matter. It's not relevant to the problem as long as I keep it low. If the Mach number in the tunnel happens to be 7 and the Mach number in the flight conditions happens to be 0.1, then you're going to have obviously very different flow properties. But if both of them are pretty low, below 0.3, it doesn't matter if the tunnel is 0.1 and the real flight conditions 0.2, because the Mach number is not having an effect on the flow field. It's not having an effect on the drag or the lift. And so in that case, you just drop it from the equation and you focus on getting your Reynolds either right or close, and definitely getting your angle of attack correct. And so when we get into foils, we'll study a bit more, when is Reynolds number really important and when is it not? And that is a really important question to get at. And there are some differences in whether you're talking about lift or drag. When it comes to drag, Reynolds number is essentially always important when you're thinking about skin friction. It's directly dependent on that Reynolds number. When it comes to lift, the Reynolds number is really not as important, particularly at low angles of attack. What's driving that lift is the pressure distribution. What's driving that pressure distribution is the shape of the wing and the angle of attack. And you're going to control those. And you might have the Reynolds number wrong, but it's not going to really mess too much with your pressure distribution unless you're near stall, or unless you're at extremely different Reynolds numbers. Then it isn't a critical matter, and we'll come to see that when we get into more about foils. I want to caution you when thinking about drag coefficients. You had a question in class about a vehicle, and what is used by convention for that reference area that goes in the denominator. So it's always the dynamic pressure, free stream dynamic pressure. The characteristic area or characteristic length scale squared depends on the industry. really. And so for ships, you use by convention, the wetted surface area of the ship. The wetted part of the ship touching the ocean. For the wing, we use, as we mentioned, the planform area. And so these are sort of areas that are of the surface itself. When it comes to, and these are bodies that really are skin friction dominated. So you can see here, this isn't a minus, it's a tilde. The scan is not very good. So when skin friction dominates, as it would in a wing, as it kind of does in a ship, ship also have wave making as well, but we'll think about skin friction dominating. In those cases, you want to have your surface area tied into that surface somehow, because that's really what's controlling the drag. It isn't necessary. You could use a cross-sectional area, but it's better to have it tied in so that relationship is stronger that you're studying. So by convention, that is what is used. In industries, and this includes the automobile, as well as anything studying a bluff body, a body where you have lots of strong separation drag, flow over a truck, flow over a car, flow around a parachute. In those cases, that's that cross-sectional area that's really driving the drag. The details of the object, shape, if the car is twice as long but the same frontal area, its drag coefficient's pretty much going to be the same. But if you cut the frontal area of the car in half and keep the same length, you're going to have a drastically different drag on the car. So we're thinking about what the cross-sectional areas is really king for getting at the drag. And so for these industries, they use those. And again, the frontal area is basically, if you look at a car from the front, and I'm not going to be able to draw a car very well, but look at a car from the front, and you stand at infinity, and you take a picture of the car against a wall, and you cut that area out, it's that area right there. That's what's used just by convention for car shapes. So we have these two fundamental non-dimensional parameters. For wings, we'll be thinking about a wing Reynolds number. So you have the kinematic viscosity in the denominator, and the Reynolds number. If you think about pipes, you have the pipe diameter. For wings, the length scale we will use is not a diameter; it's a chord. It's the chord of the wing, and then you have your kinematic condition, your velocity, your free stream velocity, or the velocity which the plane is moving. Be cautious that unlike water or unlike a fluid. Fluids and air, as I mentioned in class, have the opposite relationship. The viscosities are the opposite relationship with temperature. In the case of we have this atmospheric variation, particularly in the density. The density is going to drop with altitude. And because nu is equal to mu over rho, and rho is dropping significantly with altitude, that means that the kinematic viscosity is going to creep up. And there are significant differences. So if you have the same wing moving the same velocity, it will have different Reynolds numbers, almost a factor of 3, higher at the ground than you will have at altitude. And so there is a Reynolds variation just purely by altitude changes, not through velocity or length scale. When you're dealing with ship hydrodynamics, you don't really think about, nu is basically a fixed number, and you're only thinking about velocity and the length of the ship affecting the Reynolds number. In the case of flight, the flow properties are varying, and so all three things are going to come into play. I just put some chord-based Reynolds numbers here so you can see the kind of range that we're dealing with. A fruit fly, the chord of a fruit fly wing is about 1 millimeter. They fly about 1 meter per second, and their Reynolds number is about 100. So it's just 2 orders of magnitude. It's a pretty small Reynolds number. And we go through all these to the dragonfly, so that's still a flying insect, to a flying bird, the albatross, to a glider, Schleicher glider, up to a typical recreational aircraft, the Cessna 172, up to a Boeing, flying at 11 kilometers. So I put this last one actually at altitude, so I have the nu for the kinematic viscosity relative to the altitude. And you have the associated characteristic speeds of those aircraft. So you have the wing chords, characteristic speeds, kinematic viscosities, and here are your Reynolds numbers. So it's a huge range of Reynolds numbers from the fruit fly up to the 747. And this is the 747 wing, not the fuselage. This is the wing Reynolds number. So if you consider this flow regime, it is this variation. It's an enormous variation in flow regimes. And what the fruit fly experiences at those tiny Reynolds numbers is a very different kind of flow than what the Boeing experiences at something like a 50 million. So there is a true Reynolds dependency, of course, on the drag, but there will also be one on a lift, as well. When we look at the pressure distributions in a couple of classes, we'll see that in our sort of range, if we're mucking around, say in this range right here, looking at the lift on the wing, there's not that much change to the lift coefficient when you vary the Reynolds number across a range like that. It's a pretty small change, so it's sort of Reynolds insensitive. If you allow yourself to range through this entire range, you will find out that you have Reynolds sensitivity to your drag, of course, as you always do, but also to your lift. We'll look at that more in class. The other important one is the Mach number, which is simply this ratio as you study the aircraft velocity through the air divided by the speed of sound. We have the two speed of sounds that we calculate in class, and these are good to sort of keep in the back of your head, as is density at 11,000, density at sea level, and pressures. The Mach number of a fruit fly, again, very, 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 very low. So Mach number or compressible effects do not affect the fly at all, other than the noise it makes. But in terms of the actual flight, you have a Cessna is still in really a weakly compressible range. So the cutoff, again, the rule of thumb is 0.3, Mach 0.3. Once you get above that, you have to start considering compressible effects. Once you're below that, you can ignore them. But that is just a rule of thumb. And as you move up, you start seeing in the World War II vehicles, they were in the compressible range. So still subsonic, flying subsonically, but they're flying fast enough that you have to consider compressibility effects when you consider their flow regime and make calculations of the forces on these vehicles. Once you get up to the next regime, I put a B-2 bomber here, but this could easily be any commercial aircraft that flies. You're in modern aircraft that like a B-2 bomber or a 777. You're in the Mach mid to low or low to mid Mach 0.8s, and these are considered transonic because there are portions of the aircraft that are experiencing supersonic flow, namely the flow over the wings. But the aircraft itself, the flight speed or flight Mach number of the aircraft itself, is still subsonic. Then you move to a new regime where you are supersonic, everything, or where the vehicle itself is, I should say, is supersonic. Again, these are all compressible, so you have the idea of compressible subsonic, compressible transonic, compressible supersonic, and we will treat those in 2 separate weeks after spring break, how we deal with these. There aren't many vehicles that spend a lot of time at supersonic speed, and they call these supercruise vehicles. They're designed to fly for more than, say, a minute at supersonic speeds. The new F-22 is as such. The Europeans have a fighter jet, I forget which one, is designed for supercruise. The Concorde was designed to fly at Mach, I think it's actually 2.1, basically Mach 2. That was its designed point, and the SR-71, that is a design point. It gets up to that speed, it spends the entire flight at that speed, and then it comes down. Whereas fighter craft, they will always list a top Mach number, but typically they don't spend very much time there at all, with the exception of the few that are designed for supercruise. But they're in the list of all the vehicles that were ever made, the ones that are designed to go cruise supersonically, there's just a handful. There's maybe 10, I want to say, in the history of aircraft, because of the fuel costs. So I'll end this here. I want to do a little tutorial showing you effects of Reynolds number, and then we'll do a couple problems.